Thank you very much. Thank you for inviting me here and for attending this talk. So this is a talk about guidance, navigation, and control. So it's not a low-hanging apple in deep learning, I would say. It's something that if will ever happen, and I think pretty confident it will happen in 20 years' time or something like this. This is about giving AI the full control of the decisions on board of a spacecraft. And this is based on the fact that the original idea here is that in space, we can actually learn and choose who and what we learn from, unlike kids and children who would have their parents, and that's what they have. When we teach spacecrafts, we can actually choose the mathematical best solutions to try to imitate. And I'll hope this will become clear in a while, if I manage to change the slide. So first of all, there is a difference between all the work being done in reinforcement learning and robotic perception and action on Earth-based application in space. Space has traditionally been a great gym for physics and for purely mathematical theories to test from the very beginning. Why? Because it's empty. And while we do think and we do cope with disturbances with respect to what we have here on Earth, we can say with fairly good approximation that there are no disturbances there. There's no friction, okay? And this is a great asset. There's little stochasticity in the dynamics of a spacecraft around planets, in the dynamics of robots as well, and probes in general. The stochasticity, as far as there is no atmosphere, is very small, so we know exactly what's going on. On the other hand, in space, we do need guarantees that what we do and what we predict is correct, is going to work. We need to understand what the AI is telling us. We cannot risk to not understand. Otherwise, we would never send a spacecraft out there without having mathematical guarantees. We do need great precision. On the Earth, you go like there or there, it's okay. A robotic arm or a self-driving car, it's okay if it is 1 centimeter to the left or to the right, which with respect to the whole thing is pretty large. In space, we need to be very precise, spot on. We don't allow for much margins. And in space, we don't have much resources. We don't have computers on the satellites that can run on infinite power or be very big or things like that. So reinforcement learning, it's a good approach to tackle this type of decision-making problems, but on Earth. In space, we can do better, because in space, we have Pontryagin maximum principle that can be used, whereas on the Earth, for stochastic problems, Pontryagin doesn't apply, and we have to, therefore, try to go the other way, dynamic programming, reinforcement learning, Bellman equations. In space, we do know. So this is basically the setup and the starting of a series of researches that we started 5 years ago and that are now really delivering. So basically what we do is very simple. We generate the mathematical ground truth, the exact optimal action that a spacecraft, a system, a space agent, as we call it, has to produce. And we do this by applying Pontryagin maximum principle. So we assure mathematically to the machine precision that we have the ground truth. This is very different, for example, for imitation learning and behavior cloning on the Earth, where we usually imitate a humans or the result of a noisy simulation. In those cases, for example, from the same state, you can get different actions. In our case, we have a nice mathematical truth, and we are sure, and we have a number of mathematical guarantees on what this is, and it's basically a very complex function of the state. So that's why we apply the same type of paradigm, and we imitate the best, which is the optimal control. We clone into a network the optimal control, which gives basically from the spacecraft state, the agent space, to the optimal action. And then we can train also another network from perception to the state. This is the pose estimation that Marcus talked in the opening talk of today. And then we can put these two together, and we have an end-to-end network that goes from perception to optimal action and can and I'll show you, I think, if I can show this movie, I don't think I'm going to have time. But anyway, can drive optimally and with the required precision a number of space systems, landing, docking, interplanetary flight, and things like that. End-to-end network, which is not trained end-to-end. So we trained the state optimal action separately with imitation learning and the convolutional neural network from perception to state post-estimation on different datasets. So I'm going to talk here about the second part, from state to action. This is a simple 5-dimensional cases, doesn't matter. So what is this architecture? It's not even difficult. Why? Because we do not need strange recurrent neural network or strange memories effect, because we have triaging maximum principle data, and those data are clean. They're as clean as they get. They're noiseless. So a very simple reactive network in terms of structure and architecture will do. What we need to take care of is that the activation functions need to be smooth. So no ReLU, no discontinuity. Outputs in this case, okay, we use the still smooth function. There we can do linear and other things. But as far as everything is smooth, the network will deliver. So I'm going to go really quickly now. So the first question that I said, we need to trust the network. One of the things that we developed is a very nice methodology to be applied to any neural network. This is based on differential algebraic technique. I guess in the room there is not many people that know what differential algebra is. It is basically a way to substitute in computations to floating point numbers in a computer a function. So no longer computing with floating points, it's a new type, it's a function. A function represented by how? Well, as floating points represent real numbers, but they are obviously a different set, the functional space is represented by Taylor polynomial of high order. By doing this, basically we can, for any dynamical system that you see there, which is driven by a network, we see that x dot is equal of some kind of dynamic of the state plus the control, which is given by the decision, which is given by a network, which is smooth. I can actually expand the flow entirely and exactly. There is no round off. There is no truncation. There is no round off error here. There is only truncation. I can expand it exactly in a Taylor polynomial, the solution of the system at any time t. And therefore, if I can prove the convergence properties of this polynomial, I am proving the asymptotic stability of the neurocontrol system. So we can give mathematical guarantee that our spacecraft or our quad will land or will reach some other planet if it starts from within a ball of its starting condition. This is a completely new way of looking at neural networks output. It is difficult. I'm not saying it's easy. You guys already are doing it at first order, because when you expand the loss constant plus gradient, you're doing this at first order, and you use the gradient. This is able to go up to very high order automatically on a computer without having to derive any type of numbers. So we do that. So now we have a very nice trusted system. I'm going to show you a few applications. How much time do I have left? 6 minutes. So drone racing, this is where optimality is very important, and that's why we tested our methods here. This is time optimal control. You want to beat the human pilots here, which are the fastest racing pilot of drones with the same type of data set. So we started working on this with TU Delft, actually. Here is an example of the type of data sets that we train. This is just the loss. It goes down, and we don't care, because the loss is not really our metric. Our metric is, okay, this is like the predictions versus of the optimal control versus actually the optimal action. So the network learns the optimal control very well. This is just one case, but it's always like this. This is our metric. So you have to, after you train the network, you have to put it on a system. You have to put it and simulate it. You have to simulate the dynamical system and prove what it does. Prove that the error that you have, the mean square error you trained on, does not accumulate to catastrophic failures and everything. These are just 4 trajectories of landing of the quadcopters, which prove that it always goes to the origin stable and learns to hover. And in this case, the network was proved to do so by differential algebraic technique. So it's not only this forced simulation, we know mathematically that this is going to happen. So you can trust entirely this network to work. This is just to show you a movie of the simulation, and the Marcus showed it in the morning as well. It's during the thing, but I'm more interested to show you actually the 2 videos. So this is done with the TU Delft MAVLab, who just came back from Detroit, where they won the World Championship for drone racing. World Championship They didn't beat the human. The world championship was versus AI. So they were the fastest one to drive in a certain type of circuitry. And on the left, we see the controller that they used, which is differential flatness thing, achieving the same maneuver. And on the right now, we see the GetNet maneuver. Now, I don't know if you noticed, the right one is faster and is much more aggressive, but the fact that you see that it's very similar, it's good, because this is a network you can put on board in real time. This was in real time. It's not controlled by a computer, which is outside. This is on board of the drone. Can do the same maneuver, and it's being optimal. The other drone has no chance to beat it, because on the right, we are optimal. We're not tracking the optimal profile. We are optimal instant after instant. Same thing you can do for other dynamical system. I'm going to show you now quickly. I have a few minutes left. The same thing done for interplanetary trajectory. Database, let's go to Venus. We create a large databases of examples, optimal, again, because we want to learn from the best, going to Venus. All these databases are learned. We learn the policy. We learn also the value functions, because Pontryagin maximum principle gives us the costate, and the costates are the gradient of the value function. So we have the gradient of the value function, we have the policy, we have everything. So we can teach a network either with policy learning or with value function learning. And both actually works, and the network learns. And this is the thrust you see there in the log scales in the x-axis. So the error is very small. This is in numbers. This is how much for each databases we are mistrusting. Those numbers there are with respect to the maximum thrust. So over each 1 Newton of thrust, you would see we have an error of 2%. And that's instead, the second number is the thrust direction. So we are sub-degree. Is this good enough to get to Venus? Here we see in the case of value function and policy network. Those are starting conditions around the Earth area, changing eccentricity, inclination. It doesn't seem very large in this picture, but I guarantee you that it's huge. In terms of possibility. Usually, when we design our interplanetary trajectories, we design one only trajectory that gets to Venus from one only starting position. The fact that all that area is covered in this training, it's incredible. And the spacecraft gets to Venus orbit with the precision required by mission requirements, and the remaining few, let's say, percentages of the transfer can actually be done by simple partial derivative controller. This is mass optimal. That's the great thing about it. So we're talking about discontinuous control, mass optimal. We are sure we can get to Venus within 1% of the mass optimality without wasting therefore much time. A lot of papers have been published since we started working on this, and we're still in the process of exploring the possibilities and bringing this one level closer to the final application, which would be to run these onboard spacecrafts and let them drive themselves optimally and decide for themselves what is their path. One last thing I would like to tell you is that this network, we train them also putting as an added input neuron the optimality principle. So you can actually, with a slider during the flight of the quadcopters, change from time optimal to power optimal, change the objective of your flight, and the network will change instantaneously to the new optimal action, imitating the new optimal flight. Thank you.